This is number 2, Riemann sums, FRQ, AP practice. Let f be a function that is twice differentiable. Again, you see that word twice differentiable just means the second derivative exists. It's not 0, which means that it's a smooth curve, at least a polynomial, or at least a quadratic function. Okay. The table above gives values of the function f for selected values on the closed interval from 2 to 13. Estimate f prime of 4. So we're going to find the rate of change at 4. We don't know the exact steepness at 4, but what we can do is we can use order pairs around 4 to find the slope. So change in y over change in x. Okay, so that's going to be -2 minus 4 over 5 minus 3. So -2 minus 4 . Okay, so -6 over 2, which is -3. Okay. For part B, evaluate the definite integral from 2 to 13 of 3 minus 5f prime. Show the work that leads to your answer. Now, we have two separate terms that has a minus in between. Let's treat these like two separate problems. Okay, so let's do a definite integral from 2 to 13 of 3, and then definite integral from 2 to 13 of 5f prime. So we kind of divide and conquer when we are able to split these up. So if I split this up here, this first problem I can handle by using power rule. So we know antiderivative of 3 becomes 3x. We can evaluate our upper bound minus lower bound. So plug 13 in for x. We get 3 times 13, which is 39, minus 3 times 2, which is 6. So 39 minus 6 is 33. Okay. And for the second expression, I'm going to pull the 5 out in front. 5, definite integral from 2 to 13 of f prime. And the way we deal with f prime, the antiderivative of f prime, think about first theorem of calculus, which says that the definite integral from a to b of f prime is equal to f of b minus f of a. So we move, we take that f prime and we move it up to the f of x level because the antiderivative does that for us. So f prime becomes f of x. We plug in our upper and lower bounds. So to evaluate that, we get f of 13 minus f of 2. We go to our table of values and see if we can replace those. F of 13 is 6, f of 8 is 3. I'm sorry, f of 13 is 6 and f of 2 is 1. So we get 6 minus 1 with the 5 in front to multiply through. So 5 times 5 is 25. 33 minus 25 is equal to 8. Part C, use left Riemann sum with subintervals indicated by the data in the table to approximate the definite integral from 2 to 13. So we want to use left Riemann sum for part C. So we go to our table of values. We split them up into 4 subintervals. Each subinterval, we can subtract the x's to get the width. So 3 minus 2, that's a width of 1. 5 minus 3, that's a width of 2. 8 minus 5, that's a width of 3. 13 minus 8, that's a width of 5. Now left Riemann sum, we're just using, we're finding the areas of these rectangles to approximate that value. So the width is going to be 1, and then we want to choose the left height of each subinterval. So the width is 1, the height is going to be 1. For the second subinterval, the width is 2. The height, we want to choose the 4 because that's the left endpoint. And then for the third subinterval, that's a width of 3 and a height of -2. And then the last subinterval has a width of 5 and a height, we want to choose that 3. Total those values up, we get 18. Okay, part D, suppose that f prime of 5 is equal to 3. So in other words, the slope of the f graph at 5 has the positive slope at 3. Meanwhile, this graph is going to exhibit second derivative is less than 0, which means that it's concave down. Okay, for all the closed interval from 5 to 8. Use the line tangent to the graph at x equals 5 and show that f of 7 is less than or equal to 4. Okay. Use the secant line to show that f of 7 is greater than or equal to 4/3. Okay. So one thing that I want to point out before we move on to the details from Part D is if you have a curve that is concave down, okay, the tangent line is always going to over approximate the actual point on this curve, because it's going to sit nicely above the curve because of the way that this curve is shaped, right? It's concave down. So that's one property to keep in mind. Another property is that your secant line is always going to under approximate. It's always going to sit below the curve as long as the curve is between that secant line, right? So for this particular shape, the tangent line is going to over approximate the actual point on the curve, and the secant line is going to end up under approximating any point on this graph. Okay. So let's first find the tangent line. That's what the problem is asking for us to do here. Use the tangent line of the graph at x equals 5. So to find the tangent line, we need to use the slope in the order pair and put it into point slope form. So our slope is 3, our point is 5, -2. So y minus y1 is equal to slope, which is m, times x minus x1. Distribute the 3 through, combine like terms, we get 3x minus 17. So that's our tangent line. And we're going to plug 7 into that tangent line and see what we get. So if we plug 7 into that tangent line, we get 3 times 7, which is 21 minus 17, which is 4. So the tangent line has a y value of 4 at x equals 7. So we know that that point must be an over approximation of the actual graph. So since our graph is concave down, our tangent line is going to over approximate, so we know that f of 7, okay, must be less than 4, because our tangent line approximation has a y value of 4, and we know that tangent line sits above the curve, so the actual point must be less than 4. Okay, the next part is use the secant line. So if I want to find the equation of the secant line, I have to find the slope of the secant line and then put it into point slope form. So to find the slope of the secant line, I'm going to take these two order pairs and do change in y over change in x. That will tell me the steepness of this line. So I'm going to use 5, -2, and 8, 3. Those are the 2 points that connect the two secant lines together. So change in y over change in x, so 3 minus -2 divided by 8 minus 5, which is going to be 5/3. So that's my slope. My order pair, doesn't matter which one I choose. I can either choose 5, -2, or I can choose 8, 3. I think I can choose 5, -2 here. So y minus -2 is equal to 5/3 times x minus 5. I'm going to clean up my secant line equation. Subtract 2 from both sides. And now I have my secant line equation. I'm going to plug 7 into that secant line, because that's what we want to use that to help us make some conclusions. Use the secant line to show that f of 7 is greater than or equal to 4/3. So let's see what the secant line gives us when we plug 7 into that secant line. If I plug 7 into that secant line, I get 5/3 times 7 minus 5. 7 minus 5 is 2. 2 times 5 is 10. 10/3 minus 2 is same thing as 10/3 minus 6/3, which is equal to 4/3. So the secant line value is producing an approximation of 4/3. And if we get an approximated value of 4/3, we know that 4/3 must be less than the actual value of y of 7. And so we can make that conclusion. We're able to use the secant line to come to the conclusion that f of 7 must be greater than or equal to 4/3, or in other words, 4/3 must be less than that f of 7. F of 7 is that point on the graph is going to be above, and our secant line is going to under approximate the actual point, so therefore y of 7 is greater than 4/3.